Good afternoon, students. We had started discussing about this hybrid modeling of the transistors since yesterday's class, and here H stands for hybrid, I stands for input, R stands for reverse, F stands for forward, O stands for output, and this E stands for emitter. Here this B stands for base. Similarly, if there is C, that C stands for collector. So this is how we used to symbolically have a notation for the hybrid parameters. So HIE, hybrid input emitter. Even though those wordings are not exactly connected, we are going to utilize these symbols for the modeling of the BJT. So, continuing yesterday's discussion, from the input side, we will see a base to emitter junction. So, at the input side, we will be seeing an input impedance, and then at the input side, you will have a reverse voltage transfer ratio or reverse transfer voltage ratio. There, the output voltage is again modeled at the input. That is why we have this HRE. That is from the input side. Now at the output side, we have this current gain IC by IB. We can write it as HFE into IB. Now this is forward current ratio, forward transfer current ratio. And then again from collector to emitter, we have one admittance here, and that admittance is named as HOE. So it can be written as impedance as 1 over HOE. See, we had input impedance and output admittance in our definition of hybrid parameters. Please recall whatever we had discussed yesterday. So, based on that, we have to write HOE. Now, we have to indicate impedance at the output means we have to write 1 over HOE. So, the purpose of these hybrid parameters is that these are applicable to any operating conditions. It is not just for the quiescent conditions. Whereas the RE model was limited to the quiescent conditions. These parameters are going to be provided by the manufacturer himself. So that way, the designer's life is becoming much easier now, provided we have all these values. This was for common emitter. Similarly, for common base, taking PNP transistor as a model, we can write taking emitter as input and collector as output. And here E, HIB, and we have HRB into VEB. Here base is common. Then we have HFB into IE, and at the output we write 1 over HOB. Okay. Now, if we proceed in this manner, let us focus initially on the common emitter model. Now, if you compare this with the RE model, you will see that at the input we had that beta into RE. Instead, here we have HIE. At the output, we had beta into IB. Here we have HFE into IB. And at the output, we had R0. Here we have 1 over HOE. And in the RE model, we did not have this HRE into VCE. Okay. Now, looking at this diagram, we can directly say in relationship with the RE model, we can directly write it as beta into small re equals HIE. We can also say R0 equals 1 over HOE. And we can also say beta equals HFE. That way, these two are having their own parallels. In the sense, if the RE model is meant for a quiescent condition, hybrid model is meant for any condition, but they have relationships there. So, in the quiescent conditions, we can write that HIE equals beta into RE, and HFE equals beta, and 1 over HOE equals R0. That way, we can straight away use this model. What about this HRE into VCE? We are going to ignore this HRE into VCE. The reason is, At the output we have volts, at the input we have millivolts. As far as small signal analysis is concerned, at the input actually it is millivolts, maybe microvolts, maybe nanovolts, maybe picovolts, maybe femtovolts, maybe attovolts, maybe zeptovolts, maybe octovolts. But at the output it is volts. In such a case, this value of HRE is going to be very small. The input voltage when compared with the output voltage is going to be very small, and hence this whole term can be ignored. HRE into VCE can be ignored. So in that way, we can directly write an equivalent circuit which is as good as the RE model, where we can write the hybrid model for the transistor only with HIE, HF into IB and 1 over HOE. Now using that, we can solve all those exercises which we had solved in the first module. Okay, that is the idea here. Let me proceed. In the CE configuration, due to the high gain, HRE is a very small quantity. In addition, 1 over HOE is a very large quantity when compared to RL. Hence, considering HRE approximately equal to 0 and 1 over HOE equal to infinity, the hybrid equivalent can be written like this. You can see this hybrid equivalent, only HIE and HF into IB, even that 1 over HOE is not written here. But in practice, we don't ignore this 1 over HOE as such. If it is given, we are going to use it. If it is not given, then we will assume it as infinity. Just like in our first module, if R0 was given, we used to use it. If R0 was not given, we used to assume that it has an infinity. Same thing here. But what is told here is 1 over HOE is very large quantity when compared to RL. That means if the amplifier is having a load resistance, that load resistance will be actually much lesser than this R0 or 1 over HOE. So when these two resistances are coming in parallel, whichever is the least one, that will have the effective resistance value. So that way, if there is a RL which is much lesser, then this 1 over HOE can be completely ignored. That is the idea here. Otherwise, if it is given, we are going to use it. So we can see this model only HIE and HF into IB. So this is as good as our earlier RE model. So now in comparison this RE dash model, because Malvino calls it as RE dash, using this prime symbol or this dash indicating that it is within the transistor. Okay, that's all. So in comparison to the RE dash model, HIE equals beta into RE dash and HF equals beta AC. That is what I have been telling in the past few minutes. So now, similarly, the common base configuration can be written this way. The common base configuration can be written this way: HIB into HFB into IE, ignoring the other two counterparts. So in comparison with the RE dash model, we have HIB equals RE dash. Please recall the small signal analysis of common base model, where we had RE dash directly at the input. Now here we have HIB, and there we had alpha, here we have HFB, which means that HFB is nothing but minus alpha. Why minus alpha? In the case of BJT, we had used the current direction in the other way. Now you can see here also, in the common base model, current is going into the emitter in case of a PNP transistor, and current is going out of the collector, considering the PNP transistor here. Now, as we have shown this particular diagram as current flowing down to ground, indicating that base is at ground. So in this particular model, we can write this as HF equals minus alpha. Can you solve this exercise quickly? Someone has to solve this exercise and quickly give me the answers. Given IE equals 2.5 milliampere, HF equals 140, HOE equals 20 microsiemens. Determine the hybrid equivalent circuit. Now there are 44 students attending the class. I expect some of you to quickly find out the answers, and either you orally tell me or you put it in the chat box. Given IE is 2.5 milliampere, given HF equals 140, HOE equals 20 microsiemens. So HOE equals 20 microsiemens, determine the hybrid equivalent circuit. Quickly tell me the answer for a common emitter model. At the input you should have HIE. So tell me the input impedance, the gain factor and output impedance quickly. Okay, Sayan has given the answer 50 kilo ohms for output resistance. Yeah, that is correct. That is 1 over HOE. 1 over 20 microsiemens will be 50 kilo ohms. That is fine. What about HIE? In comparison with the RE model, HIE equals beta into RE. Now beta is nothing but HFE, that is given here. You will have to find out RE. RE is nothing but 26 millivolts divided by 2.5 milliampere, because RE is nothing but 26 millivolts divided by IE. So find out RE multiplied by the HFE, you will get HIE.
One four five six ohms.
How much?
1456.
1456. Okay, one answer is 1456 ohms. Another answer is 10.4 ohms. Let us see the answer. RE dash is 26 millivolts divided by 2.5 milliampere, that is 10.4 ohms. So, yes, Sayan has given the answer. RE dash is 10.4 ohms. Then HI equals 140 into 10.4, that is 1.46 kilo ohms. So that is correct. Who told that answer? 1456 ohms?
Lokesh.
Lokesh, very good. Your answer is also correct. Both students have given me the answer. So HI is 1.46 kilo ohms. So R naught is 1 over HOE equals 50 kilo ohms. Already Sayan had given this answer. So now we can write the hybrid equivalent circuit. The hybrid equivalent circuit is this now. At the input we have 1.46 kilo ohms, and at the output we have 140 into IB, then we have 50 kilo ohms. This is as good as our RE model. So using this particular approach, even now we can solve the exercises using hybrid parameters. Provided, let us say, HF is given, HOE is given, the emitter current is given, you can find out all other things and you can actually perform the small signal analysis using the hybrid model. So now let me see. I am giving you one more exercise now. I want you people only to quickly solve this exercise. Given HI equals 2.2 kilo ohms, let me zoom this. Okay. Given HI equals 2.2 kilo ohms, HFE equals 100, HRE is given here 4 into 10 power minus 4. Of course, you can ignore this also, or if you want to use it, you can use this also. 4 into 10 power minus 4 is actually negligible. HOE is 25 microsiemens. Now sketch the following CE hybrid model, CERE dash model, CBRE dash model, CB hybrid model. Do the first two, that is enough. The second, third and fourth I will show you. Common base RE dash model, common base hybrid model I am going to show you. Just draw that common emitter hybrid model and common emitter RE dash model. Common emitter hybrid model is obvious now. We have HIE 2.2 kilo ohms. At the output we have HFE into IB, and we have at the input we have HRE into VCE, and at the output we have 1 over HOE. So you don't have to write the common emitter hybrid model. That is obvious. That diagram I will show you later on. But I want you to solve for the CERE dash model now. Using the given data, tell me the value of RE. 40 kilo ohms for output. Yeah, that is fine. HOE is 25 microsiemens. So 1 over 24 microsiemens is 40 kilo ohms. What about RE? RE or RE dash, both are one and the same. Malvino uses RE dash, whereas Boyle stud uses RE itself. Anyhow, both are in the smaller case. So RE is 22 ohms. Mitesh has given the answer. Correct. HIE is 2.2 kilo ohms. We know that HIE is nothing but beta into RE. Beta is nothing but HFE. So RE is 2.2 kilo ohms divided by 100. That is 2200 divided by 100 is 22. So we can straight away write the model now. You can see here 1 over HOE is 1 over 25 microsiemens is 40 kilo ohms. RE dash is 2.2 kilo ohms by 100 is 22 ohms, and alpha is 100 by 101. Alpha is nothing but beta by 1 plus beta. That beta is nothing but HFE. So alpha is 0.99. So we can write this model, hybrid model. At the input we have HIE 2.2 kilo ohms and we have 0.0004 VCE. This is given. HRE is given as 4 into 10 power minus 4. We can write it directly. Now here we have 100 into IB. HFE is given as 100. And the output we can write 40 kilo ohms. This is the hybrid model. Now we can write the RE model. RE model, we need not write this at all. This does not exist. This voltage source at the input does not exist in case of RE model. So we can directly write it as 2.2 kilo ohms. That itself is HIE. And we can write this 100 into IB. And we can write this 40 kilo ohms. Fine. Now coming to the common base. In the common base, we write it as, here we write it as RE itself. Let me admit the student. Okay. In the common base model, we write it as Re itself, that is 22 ohms. And at the output, we write alpha into IE. Alpha we have found out to be 0.99 IE. Now, this is the hybrid model. Finally, the Re model is also the same. We can write 22 ohms and, sorry, this is the hybrid model. What is the order given here? Common base Re dash model, common base hybrid model, correct. So now C is, this is Re model, where we consider the current direction same. But in the hybrid model, we have been taking the current direction in the reverse way. So we can write minus 0.9 into IE. This way we can write the equivalent diagrams or equivalent models for all these four. HR is not considered in the hybrid equivalent circuit as it is very low. Okay, but H0 is considered as it occurs in parallel with RL. In this example, RL was not given. That is why we have considered H0 as it is given here. Whenever it is given, let us consider that. That is the point here. Now let us apply this hybrid model for our regular circuitry. Okay. Now look at the circuitry. We have written the base bias or fixed bias. I have not written the circuit diagram now. You will have to visualize the circuit diagram of the base bias. I had told you that by keeping on looking at these diagrams, now you must be able to visualize these circuit diagrams whenever you recall them or whenever you take out from your memory. So now you see, at the input we have the base resistance RB, and at the input we have this HIE, and at the output we have HFE into IB, then we have 1 over HOE. So let me annotate. Now from this side till this side, this much is the hybrid model of the transistor itself, common emitter model with the base bias. So at the base you used to have a resistor connected to VCC, and at the collector you used to have a resistor connected to VCC. So as VCC is AC ground, we connect RB here. Then let me admit the student. Okay, and then as RC is also connected to AC ground, we connect this RC in parallel. So now we can write the expressions for the hybrid modeling of the base bias. We can directly write Zi equals RB in parallel with HIE. In our RE model, we had the expression RB in parallel with beta into RE. Here we write RB in parallel with HIE. Similarly for Z0, it is RC in parallel with 1 over HOE. In our RE model, we used to write it as RC in parallel with the small R0. R0 used to be given as an impedance there. Here, HOE is given as an admittance there. That is how we have this expression Z0 equals RC in parallel with 1 over HOE. So, you will have to remember both of these models from now on. We will be comparing both of them. In fact, for low frequency and high frequency analysis of the BJT and JFET circuits, we are going to utilize the hybrid model only. The reason is, hybrid model is useful for all quiescent conditions as it is given by the manufacturer himself for the given conditions. So let me proceed. Now we have to find out an expression for output gain. So we know that V0 is minus of I0 into Z0, output current into output impedance. That Z0 is nothing but RC parallel with 1 over HOE. So we can write this minus I0 is what? Minus HFE into IB into Z0. Now we can write AV equals V0 by VI. That V0 is minus HFE into, we can write in terms of IB. IB is VI by HIE, right? Input voltage is VI, we have this HIE here. We are excluding the RB there because this capital RB is for DC analysis, not for AC analysis. It was meant for setting up the Q point in the middle of the load line. Whereas for AC analysis, the AC signal is across the base itself. So we consider that way. So VI by HIE into Z0 divided by VI, VI gets cancelled. The answer is minus HFE into Z naught divided by HIE. So if at all we have to write the expression for output gain, AV is minus of HFE into RC parallel with 1 over HOE divided by HIE. Now relate this with the RE model. What was the equation for the voltage gain in the regular small RE model for base bias? Anybody recalls? Anybody recalls? Fine. You are not recalling. It was minus of capital RC parallel with small r naught divided by small re. In other words, it was minus of z naught divided by small re. Now here we have minus of HFE into RC parallel with 1 over HOE divided by HIE. Actually, it boils down to the same thing. If we simplify this in terms of the RE model, we get the same expression. But here our problem is that we have 1 over HOE, we have HIE, we don't have RE. So even though the formula boils down to the same expression, we will have to express it in terms of the hybrid parameters only. So you will have to remember this AV equals minus of HFE into, you can remember this itself as Z naught itself, right? HFE into Z naught divided by HIE. There it used to be Z naught divided by small re. Now HIE contains beta into re, HFE itself is beta, so beta gets cancelled. So it is actually Z naught divided by small re itself. But we cannot write it that way in the hybrid modeling. So the easy way to remember is AV equals minus of HFE into Z naught divided by HIE. Okay, that is the expression for voltage gain in terms of hybrid parameters for the base bias. Now for the voltage divider bias, what is the difference? The only difference is at the input you will have R1 parallel with R2, just like our fixed voltage divider bias circuitry with RE model we had used it in the first module. So instead of RB we have now R1 parallel with R2. So there we had Zi equals R1 parallel with R2 parallel with beta into RE. Here we have R1 parallel with R2 parallel with HIE. Z0 and AV are same as that of the base bias. Why? Because at the output side is concerned, we have an emitter resistor connected with the bypass capacitor. So that emitter resistor will be excluded from the small signal analysis. So you will have the same circuit as that of the base bias circuit at the output side. Now, can you quickly solve this exercise? For the network shown, determine Zi, Z0, AV and AI. Also determine RE dash and compare beta RE dash with HIE. Can you quickly compute the answers and tell me? Zi, Z0, AV and AI. How to solve for AI, that I only will show you later on. Now can you quickly tell me the answer for at least Zi and Z0? I'm waiting for the answer. You can see at the right side the values are given. HF is given 180, HI is given 2.75 kilo ohms, HOE is given 25 microsiemens. So sine is giving the answer. Zi is 2.166 kilo ohms. Okay, 68 kilo ohms in parallel with 12 kilo ohms in parallel with 2.75 kilo ohms. Okay, let me verify the answer. I feel it is correct only. Let me show you the correct answer later on. So Zi is 2.17 kilo ohms. What about Z0? Okay, Sayan is given the answer. Z naught is 2.08 kilo ohms. That is 2.2 kilo ohms in parallel with 1 over 25 microsiemens. 1 over 25 microsiemens is 40 kilo ohms. So 2.2 kilo ohms in parallel with 40 kilo ohms will be 2.08 kilo ohms. Let me show you the answer. Now the hybrid model is this. We can write the hybrid model this way: 68 kilo parallel with 12 kilo parallel 2.75k, and we have HFE given as 180 into IB. HOE is 25 microsiemens, 1 over 25 microsiemens, and RC is 2.2 kilo ohms. So ZI is 68k in parallel with 12k in parallel with 2.75k, that is 2.17 kilo ohms. So your answer is correct. Now Z naught is 2.2k in parallel with 1 over 25 micro equals 2.08 kilo ohms. So your both answers are correct, Sayan. Very good. Now let me proceed to show you the answers for voltage gain, and we are finding out the RE from the given circuit. Let us see. Why he is asking us to find out RE separately and compare it with beta RE dash? Because we can find out the RE dash directly from this circuit, right? By the DC analysis, we can directly find out RE dash, and we can find out beta RE dash. He wants us to compare the RE model with the hybrid model. Hybrid model is given by the manufacturer. RE model is established by the designer himself or herself. We are going to obtain the value for RE. So we can apply the approximate analysis here. We can find out the value of emitter current. We can find out the value of RE. Then we can compare it with this. That is why the circuit diagram is given. Let us see how accurate we are in this computation. So now AV is minus 180 into 2.08k by 2.75k. Remember this, AV is minus HFE into Z0 divided by HIE. So minus 180 into 2.08k was Z0 divided by HIE is 2.75k. We get the voltage gain as minus 136. Now AI, let me mute everyone. Okay, AI is now voltage gain itself into the ratio of the resistances. We can find out the current gain, because current gain is proportional to this voltage gain along with the impedances, right? So we can write AI equals minus 136 into 2.17k was ZI and 2.2k is RC. So current gain is minus 134. When we calculate the current gain, we can actually ignore that 1 over 25 microsiemens because it is internal. Whereas this 2.17k is going to 17k input impedance is going to affect the input signal as well. But as far as the output is concerned, this is 1 over 25 microsiemens or 25 microsiemens itself can be ignored at the output side. So we can directly write ZI divided by RC. See that the input side at the output side into this voltage gain is going to be current gain. Current gain is minus 134. Okay, actually current gain is nothing but what? Output current divided by input current, right? Now output current and input current are related with output resistance and input resistance, right? So that way we have this ratio, input resistance and output resistance. And then we have the voltage gain between output and input. That is how they are matching. Anyhow, if you reverse this way, if you reverse this equation, that is V by I or AV by AI, that is actually V by I. V by I equals R only, that is the ratio of the resistances. So that way we get the current gain as minus 134. I have been telling you earlier that common emitter model is going to give us voltage gain as well as current gain. That is why we use common emitter model only for the maximum extent. Let me proceed further for calculating the RE dash. Now we can find out IE is VBB minus VBE divided by RE. Remember all the DC analysis expressions. Those students who have not been studying the module 1 and module 2, at least from now on you have to start studying module 1 and module 2. Otherwise, this module 3, module 4 and module 5 will be the next part of the movie for you. Unless you have watched the first part of the movie, after you come, after interval, whatever is the movie that is going on, you may not be able to understand the story. Same way, those students who have not been attentive to the classes or who have not been studying till now, at least now you have to start studying all those previous modules. Otherwise, I am telling you that it will be very difficult for you at the end of the semester. Unless you study all these courses thoroughly in the whole of the semester, it is going to become very difficult for you. I have been telling you, don't take the studies of second year BE lightly. Second year BE courses are not easy as the first year BE courses. You are in the core course now. You are in the core domain now. You are in the core engineering program now. All you students have to remember these things. Anyway, let me stop my advices. You may get irritated. Let me go back to my lesson. IE equals VBB minus VBE divided by RE. We can directly find out VBB. We can apply approximate analysis here directly. Now, even though beta is not given, beta into RE must be greater than or equal to 10 into R2, right? Beta is 180 itself. 180 into 1.2K will be naturally greater than 10 into R2. You can find out 180 into 1.2K will be actually greater than this 12K into 10. This will be greater than 180 into 1.2K will be greater than 120 kilo ohms. That is obvious here just by looking at these values, just by a visual observation, you will find out that we can apply the approximate analysis here. So, by the approximate analysis, we already have this VBB. VBB is directly found out as 2.4, 2.4 minus 0.7 divided by RE 1.2K is 1.42 milliamps. I have not shown you the other steps here. How to find VBB? You must be knowing that by now. So, IE is 1.42 milliamperes. When IE is 1.42 milliamperes, you can find out RE dash as 26 milli divided by 1.42 milli, that is 18.31 ohms. Now, beta into RE dash, beta is nothing but HFE. HFE into RE dash is 3.29 kilo ohms. Now, compare this with HIE. Beta into RE dash is now greater than HIE. What was the value of HIE given? HIE given was 2.75 kilo ohms, right? You can see this here. HIE given is 2.75 kilo ohms. And we get beta into RE dash as 3.29 kilo ohms, which means beta into RE dash is greater than HIE. Now, which one to follow? Whether to follow the RE model or whether to follow the hybrid model, which one to follow? Can any of you tell me? Can any of you tell me? We got a discrepancy here. Till now we have been assuming that beta into RE equals HIE. But in this exercise we have found that beta into RE dash is greater than HIE. Now, should we follow hybrid model? Should we follow RE model? Which one we should follow is my question. Can anybody answer?
Equal only for Q point, right?
Yeah. Yeah, it is for Q point only. But the question is, we have this difference now. Even at the Q point, which one to follow? Mitesh is telling hybrid. Tell me why. Tell me why. Yes, it is hybrid only. Okay. Yeah, let us say he's typing the answer because we approximate HFE in RE model. Right, very good, excellent. See, here we have taken beta from where? We have taken beta from hybrid model only, right? Actually, we don't have the beta as such here. Beta itself is HFE given by the manufacturer himself. So, it is better that whatever the manufacturer gives, that itself we follow instead of we applying our intelligence or brain for solving these problems. The RE model will be useful only when you don't have the manufacturer's data. For example, let us say you are using a device for which you don't have the data sheet or you don't have the manufacturer's data given. At that time, we can use RE model. Otherwise, it is always the hybrid model that is accurate. We approximated HF equals beta only there, right? So naturally, it is better that we follow hybrid model only. That is when we get this difference. So that way we can say that the RE model is not really very reliable because we deduce it based on our own calculations and our own conditions of the our own working conditions of the circuitry, right? Whereas the hybrid model is given for the device itself. That way hybrid model is more reliable. That is the conclusion here. Now because of this fact only, in all our future frequency analysis, we are going to use hybrid model itself. That is the point. But why we studied RE model? Because it was easy to study in the first module. If at all I would have taught you this hybrid model in the beginning itself, you would become heavily confused. That is why it was kept later on. Fine. Let me proceed now. Okay, let me stop with this particular topic for today. I am going to discuss some more circuits in the next class and we are going to see how to apply the hybrid model for those particular circuits. And right now I have posted all the quiz links in the Google class, and strictly you will have to give the quiz answers only for the particular links of those sets, and I have given the details there for whichever USN number ending with whatever. It is like your assignment questions only. In assignments, we had those sets for different USN numbers. Same way here also, the quiz is for different USN numbers. Strictly solve only the link that is meant for you. Don't try to solve the other links as such. Otherwise, the quiz will be taken as invalid for you. We had relaxed it in the first quiz because even though in the first quiz I had told it explicitly, I had given it explicitly that from USN from 0 till 25, then 26 till 50 and 51 onwards. Still many students did not follow that norm. But at that time, I relaxed it, saying or thinking that it is the first time for you in this way. But now you already are familiar with the system. You will have to follow the system. Please follow the norms. Don't bypass these guidelines. And you can go back to the Google class. You can click on those links to give the answers. No classroom update came. It is going to come now. Don't worry. There is still time. It is going to come in a few minutes. Don't worry. I have scheduled it. If it has not yet come, now I am going to immediately schedule it. Don't worry, wait there. There is still time. I am going to end this class now. See you in the next class. Bye-bye.